Hi, Biology Bites, Roy Treveline here. Next Sacred Lab for AP Bio. What we're dealing with today is a semi-permeable membrane. Mrs. Treveline's egg I'm going to take out of the vinegar. If you look close, the shell is almost completely off. I'm rubbing more of it off as we speak. It's rubbery, soft and rubbery. You're going to make an egg just like this. You're going to remove the shell. Mrs. Treveline, this is in vinegar, you said, right?
Correct.
What do you think's attacking those shell particles, the calcium on there? Any ideas? Would it be hydrogen or would it be hydroxides if it's an acid vinegar?
Hydroxides.
Oh,
No, a hydrogen.
that's the first one she got wrong.
Yeah, I know.
Yeah. The hydrogen are attacking the calcium.
Yes.
And they're destroying that shell. We're going to be left with a semi-permeable membrane. Now, what we're talking about today is osmosis, the diffusion of water through a semi-permeable membrane. The key to remember for all passive transport, whether it's diffusion or osmosis, is things go from high concentration to low. So when I say high to low, that's what it means. Things do that naturally, right? If you brought in a pizza, you didn't have to see the pizza to know there's a hot pizza in the room, right? The pizza particles go from the hot pizza up my nose. They go from a high concentration on the pizza to a low concentration in my nose. Never, ever in a million years do the pizza molecules go from my nose back to the pizza. Well, unless I sneezed on it. All right, everything goes from high to low. This is this idea of entropy, second law of thermodynamics. And by semi-permeable membrane, you also hear differentially permeable. It means it lets certain things in and out. We're going to say that large and charged have a hard time getting through the cell membrane. And including this egg membrane, large and charged, like that it rhymes, are going to have a hard time getting through the membrane. Ipso facto, right? Small and uncharged particles can go right through. Yeah. I don't remember the other ones. I just remember large and charged. Right? Makes sense. What we're going to talk about today is water potential. I forgot. What
Psi.
Psi. Thank you. This Greek symbol, I always forget that. There's a pressure potential. That's a physical pressure from the outside. And there's a solute potential. Normally, this is going to be zero for us. What we're really going to be worried about here is this solute potential. Wherever there's a lot of solute, there's always going to be less water. You sickos out there that put salt on a slug, that's basically what we're doing today. If you put salt on a slug, it's going to increase the solute potential. It's a negative number. I'll explain why later. But this negative number, the bigger that negative number, the lower the water potential. The bigger negative number of the solute potential is going to create a lower water potential. Water is always going to go from high to low, just like everything else. Put simply, wherever there's a lot of solute, there's less water. So if you put salt on a slug, there's more water in the slug than outside the slug. There's a lot of salt outside, not a lot of water. The water rushes out of the slug. Water goes from a high concentration in the slug to a low concentration out of the slug.
And kills it.
And kills it.
Don't do that.
Mrs. Treveline, what would happen if we put that slug in 100% water? What do you think?
It would get bigger. It
would get bigger because water goes from high to low. Where's the low water potential now? Inside the slug. Water will rush into that slug. The slug will get bigger, right? And we're doing the same with the eggs today. I'm going to take Mrs. Treveline's egg one more time. It's a semi-permeable membrane sitting in that vinegar. We're going to take the shell off and we're going to change the solute potential to different solutions. Now the solution I've put my egg in, this is my egg here, is corn syrup. Corn syrup is a polysaccharide, big molecule. Large and charged have a hard time getting through the cell membrane. So will this go through the cell membrane? No, it's going to act like a solute outside of the egg cell. Just like salt on a slug, water is going to go towards the corn syrup. Wherever the corn syrup there is, there's less water. The lower the water potential, water will rush that way. Ms. Treveline's nodding yes. Okay, good. She's my barometer here. How are we doing on time, Ms. Treveline?
For 5 minutes.
Ooh. Okay, so I'm going to take this guy out. He was at 76 grams when I had my guy in vinegar. I'm going to try not to break him, and be careful when you do this, because it is a mess. It's a regular egg. It wasn't boiled or anything. And I'm going to put it on the scale. It's been sitting in that syrup all day, what we're going to call a hypertonic solution. And look at that. It lost 6 grams. This could be the new diet. Whatever. 76? 5 grams. Yeah, thanks, Sister. Hey, it's doing its trick, right? The water went out of the egg and in towards the syrup. Now, we know that some water is going back and forth, right? But I get tired of saying that there's more water leaving the egg than entering the egg. But there is a little water entering the egg. This is at about 80% corn syrup. And what I did is I just filled my little graduated cylinder up to 100, and 80 of it was corn syrup and 20 of it was water, right? It's not technically correct, but for our lab, and since the situation we're in, this is as good as it's going to get, right? Now, the solution we're in is hypertonic. This is hypertonic to the egg because there's more solute. Water rushes out of the egg. Hypotonic would be if I take my egg and stick it in 100% fresh water. And some of you will do that. A hypotonic solution is going to let water rush into the egg. Now, when I was in school, I got to tell this story very quickly. I got these mixed up. My teacher explained it one way, and when I went home and looked in the book, it was the exact opposite. And I was dumb back then. I didn't ask questions, and I should have. But what I failed to realize is these adjectives describe both the cell and the environment. If my egg is hypotonic, low solute, then my environment is hypertonic. I didn't realize those adjectives could describe both the cell and the environment. How we do it on time?
7.
7. Woo! We're going to cut it close today. Now, what we are looking for is isotonic. Aren't we all, right? Don't we all want to just be equal? In a solute concentration that's equal on outside and on the inside. That would be a beautiful thing. So what we're going to do is we're going to try different molarities or different percentage of sucrose. And actually, we're going to use starch. I should change this to corn syrup. We're going to look at different percentages of corn syrup, starch, big polysaccharides, and we're going to adjust it accordingly. Now, I'm here at 0.8, and if you'll notice, my egg lost a lot of mass, right? But if I put it in 0.2, right here, it gained mass. What I'm looking for is the sweet spot. Right where every water molecule that enters, one will leave. I want the solute concentration of the egg to be equal to the environment, right? And we call that isotonic, when the solute on the inside is equal to the solute on the outside. Now, what we can do is crunch the numbers and figure out literally what the solute concentration of that egg is. If we look here, it looks like at what would you say, Ms. Treveline? 0.2?
5.
No, not that'd be halfway.
0.2.
Oh,
no.
No, there's a 0.5 here. Okay, yeah, 0.25. I agree. We're going to crunch that with a couple of constants. And when we multiply those numbers together, come out a negative number. And it's going to give me the solute potential of that egg, right? Here, I'm thinking it's like 20%. In other words, when 20% of the environment is sucrose and the egg is 20% approximately, then there'll be an equal amount of water entering and leaving because there won't be a high water potential and a low water potential. They'll reach what we call equilibrium. Ms. Treveline's wrinkling her head at me. What do you think about that?
So does some of the corn syrup go in when you say 20%? Does in order for
now remember, the starch is too big. I should change that to starch. The starch is too big. The only thing that's going across that membrane is water.
Okay.
And at some point, they're going to equal each other out.
And so you'll only know that if it stays the same mass for a long time.
Yes. If it doesn't gain mass, it doesn't lose mass, that's the solute concentration we're looking for.
So this guy sitting in sucrose right now, this
Yes.
guy sitting in the corn syrup.
Yes, please.
He will keep growing and growing and growing and growing.
He is shrinking.
Oh, yeah.
There's more solute outside. Water will go out until it reaches equilibrium, right? He'll lose enough mass, enough water will come rushing out of there until the water on the outside equals the water on the inside. But yeah, I think you're right. I think he's still shrinking a bunch. We'll know because he'll be done. When he stops losing mass, we know he reached equilibrium. It's just the water moving across that semi-permeable membrane. It's permeable to the water, but not to the starch. Starch is really big. Water is really small. How are we doing time?
10:20.
BioBites. See ya.